What is the sine of alpha plus beta? Sine alpha, cosine beta, plus cosine alpha, whoops, times sine beta. You weren't even looking at your notes. Unless you were really quick. Nice job. Maybe you use sine and cosine a lot more for some reason. And you forget the identity for the sine of alpha plus beta. Well, tangent is sine over cosine. So the tangent of alpha plus beta is the sine of alpha plus beta over the cosine of alpha plus beta. Now you have to have, at a minimum, these two identities under your back pocket. And then that is going to be the sine of alpha plus beta is the sine of the first, cosine of the second, plus cosine of the first, sine of the second, over the cosine of two angles added together, which is cosine of the first, cosine of the second, minus sine of the first, sine of the second. If you use first and second, no matter whether it's alpha, beta, or in 30 degrees and 45 degrees, if you say the exact same thing over and over again, you know, I do that for me to help me remember that formula, or those formulas. Now, this is not what we introduced as, and what Miss wants to give me for the tangent of alpha plus beta, but let's say, and I know you're prepared for this, don't give me the whole thing, but maybe you're a little unsure about what this identity is. Maybe you know what the identity is, but you're not sure of the plus and minus nature of the numerator and denominator. What is the first term in the denominator?
It would be 1.
If you at least know there's a fraction, the first term in the denominator is 1. If you happen to forget something, or even if you're just unsure of a sign somewhere, please remember that we are preparing to take AP Calculus next year. And AP Calculus, I know that's a year and a half away, but you have to be able to memorize what you need to memorize and recreate any identities, formulas, concepts that you need if you happen to forget them, because when it comes time to take the AP test at the end of AP Calculus, you get nothing related to calculus. So all of that knowledge needs to be in your brain. You need to use it enough, repeat it enough to have it, you know, ingrained into your memory, and that you have that full comprehension. So sine over cosine, this first term in the denominator of cosine alpha, cosine beta needs to become, like we said, 1. Well, think of like adding fractions. When you add fractions and you find those common denominators, you multiply a fraction by a version of 1 to create those common denominators. Maybe you multiply a fraction by 2 over 2 to make a common denominator of 10 or something like that. So knowing that this first term in the denominator needs to be 1, knowing that cosine alpha, cosine beta needs to be divided by cosine alpha, cosine beta to create that first term of 1, you can multiply the numerator and denominator by 1 over cosine alpha, cosine beta. And I wouldn't call this a proof necessarily, because I didn't give you an identity and say, you know, show this identity true. It's more like maybe a simplification example. But we are effectively proving the sum identity for tangent. So when we multiply the numerator and denominator by 1 over cosine alpha, cosine beta, we have sine alpha, cosine beta over cosine alpha, cosine beta. Then we have plus cosine alpha, sine beta. Divided by cosine alpha, cosine beta. That's our new numerator. Our denominator now is cosine alpha cosine beta divided by cosine alpha cosine beta minus sine alpha sine beta over cosine alpha cosine beta. This simplification or rewriting step was not random. It helped us by telling us the first term in the denominator is 1. And what do we have? Cosine beta divided by cosine beta is 1, giving us our sine alpha over cosine alpha, which is tangent. We have the plus in the numerator. That sign is staying the same because in the numerator we have the sum of the sine of alpha plus beta. So plus the cosine alpha divided by cosine alpha cancels, and we have sine beta over cosine beta, which is tangent of beta. And then here's our 1 minus sine alpha over cosine alpha is tangent of alpha. Sine beta over cosine beta is tangent of beta. So now we have our, well, I have 5 written at the moment. We have our 5, and now our tangent alpha minus beta is the tangent of alpha minus tangent beta over 1 plus tangent alpha tangent beta. So some of the identities that are in the rest of this chapter we don't need, but we're going to learn half angle identity, double angle identity, and power reducing formulas. All of those formulas can be derived by using the sum and difference identities of sine and cosine. The proofs of these first two are pretty involved, involving a lot of Pythagorean theorem and triangles drawn and standard position angles, but if you know at least those two, you can derive everything else that's in the rest of this chapter. Let's take a look at this example. We're going to prove or verify that the sine of alpha plus beta over cosine alpha cosine beta is equal to the tangent of alpha plus tangent of beta. So what is the first thing I told you to do, making sure I get this copied correctly, what's the first thing I told you to do, or how should you start a trig proof? Yeah, start with the more complicated side. Now, we're just getting introduced to these kind of proofs, or being introduced to proofs that involve sum and difference identities. There is no wrong answer as to what side of the identity you start with. I think, honestly, the door is open to being able to start with the left or right-hand side and kind of have that same level of difficulty and probably about the same number of steps. But there is, as you can see, at least we proved the sum and difference identities for tangent, that there's a lot of math behind these sum and difference identities. So I do tend to start with the side that has that sum or difference, because that opens the door to me immediately substitute in a pretty complex equation in place of the sine of alpha plus beta, and that should open the door for a lot of math to occur. Now, if you want to start with tangent alpha plus tangent of beta, because you can write them in terms of sine and cosine, that's going to kind of naturally lead you to the right answer as well. This will be a relatively short proof, regardless of what side we start with. So I think it's kind of 50-50, but I would say start with the left-hand side. So our proof, starting with the left-hand side, is the sine of alpha plus beta over cosine alpha cosine beta. You're never going to get the two sides of an identity to match unless you get all the measurements to be in the same sort of universe. All singular angles, coming up soon, maybe even all double angles. But you certainly have a complexity going on here where you have single angles going into the cosine functions in the denominator, but in the numerator you have a sum of two angles going into the sine. So, anybody want to help me with the next step?
Just factor out sine A plus B to sine A cosine B plus cosine A sine B.
You didn't say factor, did you? Substitute.
Yeah.
Substitute. So we're going to take out the sine of alpha plus beta and replace it with, nice job, sine of the first, cosine of the second, plus cosine of the first, sine of the second, all over cosine alpha, cosine beta. What is another standout difference, a major difference between our current expression and where we want to go?
There's like two alpha word for those two
Terms.
terms.
Our final answer is tangent of alpha plus tangent of beta. There is a plus sign separating two terms. There are two terms in the numerator of this one singular fraction. So right now you have one, it's complex, but you only have one term and you want your answer to be 2. So let's undo that addition. You have a sum of two terms in the numerator with a common denominator. When you add fractions, once you add that common denominator, you just copy, right, that common denominator. So we're going to have the sine of alpha cosine beta over cosine alpha cosine beta plus the cosine of alpha sine beta over cosine alpha cosine beta. I see you doing some kind of hand motion like she's swinging a sword around. Wonder why? Why? Why ask why? What happens in the first term?
In the first term, we cancel out cosine.
Yeah, we cancel out the cosine betas. What about the second term?
We cancel out cosine alpha.
Cosine alpha. So what is sine alpha over cosine alpha? Tangent alpha. So we have the tangent of alpha plus, oh my gosh, sine beta over cosine beta is tangent of beta. Bam! All right. So really kind of only like a 2 or 3 line proof depending on how you're counting. Let's try another one. Let's take a look at this example. We have the sine of x plus y times the sine of x minus y is equal to sine of x squared minus sine of y squared. You want to start with the left or the right-hand side?
The left-hand side.
Okay, I like that idea. So you are going to have to help me with the next line. So our proof, starting with the left-hand side, is going to be the sine of x plus y times the sine of x minus y. And then what are you going to do from there after you've started with the left? What are you going to do over here?
Would you
Distribute what?
the sine
Does it look like we can distribute the sine through the parentheses?
Oh, okay, I see. So you would just substitute in for the first one. It would be sine of x.
So sine of the first,
The
x,
sine of the second, which would be cosine of y.
times the cosine of y. That's what you said and what I heard and what I said. Why did my hand write x?
And then it would be plus cosine of the second, or the first, and sine of the second.
Cool. And then that binomial now is going to, so we did that substitution. The sine of x plus y is sine of x cosine y plus cosine x sine y. And that's going to get multiplied by?
The same thing, but in the middle be minus.
Perfect. Sine of x cosine y minus cosine x sine y. What do you have any ideas what we should try to do? Just to spread them around.
If I'm
Yeah, start doing some math. Ooh, that sounded very fancy. Distribute, and you said what? Difference of squares. So since you have like a plus b, okay, we have sine x cosine y, and in the second two-term expression, we have a sine x cosine y. In the second term of the first factor, let's call it cosine x sine y. The second term of the second factor is again cosine x sine y. So it's a plus b times a minus b. So there is a recognition here by Trig that this is a difference of squares pattern. So when he goes to distribute all this out, you probably are not going to write three terms. When you have conjugate pairs, that's the only two binomials that multiply together to give you two terms. Every other multiplication of two binomials, okay, these are not polynomials, but is going to give you three terms. So what's this going to multiply out to? Sine of x squared cosine of y squared minus cosine of x squared times sine of y squared. Okay? There's 4 steps to this multiplication, right? But you only have to worry about 2 of them because the middle term is going to cancel out with this difference of squares pattern. Some of you might see this right away, but I'm going to pause. Think about our current expression and how it is different to the answer, right? That you should always be doing that. We are here now. We've done some substitution using sum and difference identities, and we did the math that developed from it. We might be going in the right direction. We might not. We're here now, though. What's the same and what's different about where we are and where we're going? So our current expression has cosine functions in them, and our answer does not. So how might we remove these cosine squared functions and basically replace them with sine functions? Is there an identity that we know that relates sine squared and cosine squared? Sine squared, as I stand in front of you, as you're trying to tell me what to write. Sine of sine squared x plus cosine squared x is equal to 1. So then we can say cosine, this is what you were starting to say, cosine of x squared is what? 1 minus sine squared x. Perfect. So whenever you have a proof that has a lot of powers of 2 all over the place, look for those connections, those 3 Pythagorean identities that relates sine and cosine squared and cosine squared, tangent squared and secant squared, and what? Cotangent squared and cosecant squared. Nice non-choral answer. Come on, people. So we're going to do substitution again. So we have sine of x squared times cosine of y squared, which is going to be 1 minus sine of y squared minus, and then cosine squared of x coming out, being replaced with its version in terms of sine. So we have 1 minus sine of x squared times sine squared. This is kind of fun. We finally did a proof that's not like just 2 or 3 lines long. Distribute again. Okay, so let's see what happens when we do this. Hopefully something nice, because I hopefully don't do all this work and realize we need to back up and do something else. We're going to distribute. We'll have to be careful of this negative sign of y squared. I don't mess that up. So we have sine of x squared times 1 is sine of x squared. And then minus sine of x squared times sine of y squared. Okay, now this is negative sine of y squared times 1 is negative sine of y squared. And negative times negative is positive. We have sine of y. I'm not sure if the x or y should go first. Of course, multiplication is commutative, so it really doesn't matter. But sine of y squared, if I just slow down, I could do this faster. Sine of x squared. Help me out.
You could rewrite the last term as sine squared x multiplied with sine squared y. Just like rearrange it and then you can combine it with.
Okay. Multiplication is commutative, but is telling me if I put the x and y first, we'd kind of see something nice happen. Over here we have sine of x squared, so let's go ahead and just write the sine of x squared first. We have a sine of y squared, so we have a sine of y squared. And this is looking awfully ugly, but yeah, these are like terms. Right? These are like terms. Coefficients are opposite numbers. That's -1. This is +1. Those are going to add together to give you 0. Oh my gosh, I thought we were going down a wrong path, and we are done. We have sine of x squared minus, look at there, minus sine of y squared. Bam! Nice teamwork. I like it. Did I lose anybody's point? No. So your identities, to apply these identities, or I mean, we could talk about reciprocal identities and cofunctions and properties of even and odd, but right now, in terms of like doing trig proofs, I'm going to shoot myself in the foot because there might be something involving cofunctions or even and odd properties of trig functions, but the main sort of like super important identities that are not just super fundamental, like reciprocal identities, is your 6 sum and difference and your 3 Pythagorean identities, which is sine squared plus cosine squared is equal to 1. 1 plus tangent squared theta is equal to secant squared theta. 1 plus cotangent squared theta is equal to cosecant squared theta. And to use any of these, what would this be? 6 and 3, 9 identities. They have to be like an exact match. Sine squared theta plus cosine squared theta is equal to 1. We haven't learned double angle identities yet, but if I put a minus there, it's a cosine of 2 theta, like totally different. Not 0, not -1. A lot of students think if there's a minus here, this is -1. It's way more complicated than that. How about 2? I know you love it when I do that. 2 times the sine of x plus pi over 2 plus 3 tangent of pi minus x is equal to 0. And we're going to find all solutions on 0 to 2 pi. How do I isolate the variable or solve this for x? It certainly does not look anything like the equations that we solved a couple of sections ago, where we could like isolate the trig function and apply an inverse trig function to both sides. Any ideas? I'm not even sure because I haven't done this type of question since last year, so I literally do not know the process right now. How about the sine of 2 angles added together? Because right now we can't evaluate this at all. Can we rewrite this in a format that maybe we could do some unit circle evaluation?
I'm sure you could. Yeah, I don't like that. Yeah. Over there.
So the sine of, what is the x and the pi over 2? What do these two things have to be? If these two things are going into a trig function, what do they have to be? What do we put into a trig function? What do we put into a trig function? What do we put into a trig function? Why is nobody talking to me? Angles, besides 1. So let's do the sine of 2 angles added together, which is going to be 2 times the sine of x cosine of pi over 2 plus the cosine of x sine of pi over 2 plus 3 times the tangent of pi, whoops. This is the tangent of two angles being subtracted. So it's tangent of the first, tangent of pi minus, somebody said it, tangent of x over 1 plus tangent of pi, tangent of x is equal to 0. That looks disgusting. Let's see where we go. Maybe occasionally we don't do just the easy problems. What's the cosine of pi over 2? My elbow is the origin. 0. So we have 2 times sine of any, the sine of x times 0 is 0. Plus, I got simple really quick. What's the sine of pi over 2? 1. So we have 1 times cosine. So we have cosine of x plus 3 times, what's the tangent of pi? What's the coordinate over there on the unit circle? If my shoulder's the origin? Negative 1, 0. So it's y of 0 over x of negative 1, which is, y'all said it correctly, 0. I'm just verbalizing it. So we have 3 times 0 minus tangent of x over 1 plus tangent pi, tangent x, but tangent of pi is 0. You just said it. Equals 0. Okay, so now what do we have? We have 2 cosine of x minus 3 tangent of x is equal to 0. Well, we now have a much simpler looking equation. Still not simple, but simpler. We have an equation with 2 different trig functions in it. That's like an equation with 2 different variables. And you cannot solve a single equation with 2 variables unless they factor apart. So it looks like we might have a problem here. Let's write it in terms of sine and cosine and see where we go. So we have 2 cosine of x minus 3 sine of x cosine of x equals 0. Ooh, this is another fun problem. I started double checking my example here, making sure it wasn't a calculator-based problem. Thanks for the help. And you wrote it in terms of sine and cosine. What might be the next thing we try? Common denominator. So let's put this 2 cosine x over 1 and multiply the numerator and denominator by cosine of x. We're really literally just throwing, anybody know how this problem works out? Anybody done this before? No. If we get a challenge, do we just like give up? No, we're just trying, okay? We're processing and we're going until either we realize we hit a dead end or we get the right answer. So we have 2 cosine squared x minus 3 sine of x over cosine of x is equal to 0. Boy, I stumbled on a nice, fun example. We have a fraction equal to 0. What's the only way an entire fraction equals 0? The numerator is 0. If the denominator is equal to 0, it's undefined and there's no solution. If the numerator is equal to 0, what's 0 divided by 10? 0. 0 divided by 5? 0 over 100. So we could just focus on the numerator. And I know that some of us are going to have quiz grades come back to you tomorrow that you're not happy with, but we have an opportunity to remediate quiz grades with chapter test grades, and that's why we do quizzes, to give you a gauge of how well you're internalizing the math so far. This is all of a sudden a question you had in whatever section 5.2, I think it was, solving trig equations. How do we write this in terms of one trig function? Use one of the Pythagorean identities again and substitute cosine squared of x with 1 minus, whoops, that's a 3. That's not 3. 2 times 1 minus sine squared x minus 3 sine of x equals 0. Distribute the 2, and you should always have your powers go down. We have negative 2 sine squared x minus 3 sine of x plus 2. I really do not like factoring when the leading coefficient is negative, so I'm going to multiply both sides by negative 1. I sure hope this is factorable. 2 sine squared x plus 3 sine of x minus 2 equals 0. Now, I do a lot of factors of A times C that add to B and review factoring by grouping, but 2 and negative 2 are both prime. So I'm going to do a little, just jump to the answer. Factors of 2 are 2 and 1, and we have sine squared, so it's 2 sine of x and 1 sine of x. Our last constant is negative, so we need a positive and negative sign, so it's either plus here and minus here, or vice versa. We need a middle coefficient of 3. So is it plus 2 and negative 1? Or plus 1 and negative 2? Or maybe the 2 goes over here? What are our two factors? 2 times, if the 2 were here, we would get 4. If I put the 2 here, we have 2 times 2, which is 4. We need the 4 to be positive because our middle term is positive, so we need a plus 2. 2 times 2 is positive 4. We have a negative constant, so we need a plus and a minus, and so it's 2 sine of x minus 1, and sine of x plus 2 is equal to 0, and that's factored. And of course, once you get a quadratic in factored form, you set each factor equal to 0. So 2 sine of x minus 1 is 0, meaning sine of x is equal to 1/2. I'm going a little faster because you've seen this a bunch of times, and we're also running out of time. Where on the unit circle is sine 1/2? Pi over 6. Man, nice. And 5 pi over 6. And where is sine? We have sine of x is plus 2 is 0. So we have sine of x is negative 2. Where's sine negative 2? You can't get a leg over hypotenuse. You can't take a leg of a right triangle over a hypotenuse because that's sine and get a number that's outside the range of negative 1 to 1. That does not exist. And we are done. Bam! That was fun. X is pi over 6 and 5 pi over 6. That is our last example. Go to your homework. Woo, that was fun. I like that.